So we have John Joseph Marchetta today talking on modern physics. It'll be addressed to students in school. And thank you, John. Go ahead.
Yeah, and to avoid saying names, I'll just refer to students. Okay, so thanks. Thanks for giving me the opportunity to speak. I had fun putting this together. So I hope you guys enjoy. So can someone tell me what they think the most famous equation is? And there is an answer on Google. I'll write it down next. But I would like to hear what you guys are thinking. And these are the type of questions, very non kind of science.
I have read on Google that it is e raised to I pi is equal to -1 is the famous equation, but I don't associate
So you,
with it so much because I don't use it. Yeah, but I can understand the value of it.
I mean, you think my family or people outside of math will know that equation?
No.
I guess F equal to ma will be probably gravity. Many
E
people
is equal to
will
mc square probably. E is equal to mc square is the most famous.
E is
Yeah.
yeah, E is equal to mc square is another one, but I would personally think F equal to ma more people should know.
No,
So-
but Einstein was really popularized. Yeah, but that's
Very much, yeah. So
Yeah.
people don't know. Okay, people don't know what E equals mc squared is, but it's so popular that that became like you have to take a physics course in high school, or at least remember what was taught in physics to know F equals ma. But yeah, I think so many people know the E equals mc squared, and that's according to Google. This is it. So oh, I want to stop the animation. I didn't
But what
notice.
about Joanne? Have you seen this equation?
Yes, sir. I have seen it and tried to do it.
Good.
So can you tell me what this means? E, what's so I tried to give some okay, what do you think it means? What does it mean? One?
So I think if we take sun as an example, the energy produced by the sun is equal to mass of the sun and the speed of the light that reach a place and squared.
Cool. So if the sun wasn't radiating, would it be 0 then? If there was no radiation coming from the sun being released?
I don't know, sir.
Yeah, but that's a great answer. Yeah, fantastic answer. So what this means is that all objects that in fact all objects have energy, and so if I'm just sitting down normally, if I'm running, do you think I'd have more energy if I'm running than if I'm standing still? John? So this is the energy standing still, and what mass is, but just to review, if we're at one place in space, so we're on Earth, and then we weigh two objects, the heavier object has mass. But how about in outer space? Will they, if you weigh them, do you know what their weight would be? If we're in outer space? If you put them on a scale, would they weigh anything? So the answer is no, but they still have mass. So it's you could think of it as how much stuff or how many particles are in and how heavy the particles are. That's how heavy the stuff that the weights are made of, how heavy the stuff that this water bottle is made of, or how heavy the stuff the feather's made of. And I think you have a notion of speed, but speed is just how fast you go, how many seconds. So if I'm going 5 kilometers per hour, if I'm moving 5 kilometers per hour, how many kilometers will I go in 2 hours? So each hour I go 5 kilometers, and then so the first hour I travel 5 kilometers, the second hour I travel 5 kilometers. So in total I travel 10 kilometers. So in 2 hours I travel 10 kilometers. But the fact that this is the speed of light is a bit like, why use that speed out of any speed? Why don't you have the speed of the earth or the speed of an airplane that just traveled yesterday from Kerala to Mumbai? So why don't you just use any arbitrary velocity? And the reason why you pick light is because nothing can go faster than light. And maybe we can understand that in another session. Okay. So I'm going to introduce another type of energy. So we saw that this is the energy of something that's not moving. So then there is an energy for motion too. So let's take these two cars. This car, let me stop this. Okay, you see my pointer? Okay, so this car has about, you could say 200 energy. And then let's say this car is traveling the same speed, but it has twice the mass. Do you know its energy? Okay, so the motion energy depends on both the mass and the speed. So if this car is traveling at the same speed and has twice the mass, can you tell me what the energy is? If the energy of this car has 200, you could say these are called kilojoules, or just units of energy, 200 units of energy. And if the car is traveling at the same speed, but has twice the mass, what do you think its energy will be? So maybe you could take a shot in the dark and guess that its energy would be, since something more massive going the same speed will have more energy, something twice as massive would have just twice the energy. If the two objects you're comparing are going the same speed. So that guess would be correct. So actually this car having twice the mass will have twice the energy. But now you could ask, what if both cars had the same mass, but the bottom car was going twice as fast as the top car? Do you think it would still have twice the energy? The answer turns out to be negative, because the thing that I call motion energy, the proper name is kinetic energy, and that's given by just the fraction 1/2 times mass times the velocity, or you could think of it actually the speed squared. So have you seen kinetic energy before?
I don't think so, John. In 8th grade, probably. What do you say, Jovan? Like, have you seen kinetic energy already?
No, sir.
Sorry, I'm like, I should put on my camera. Okay. Did you understand the difference between the kinetic energy and the energy from E equals mc squared?
Yes, sir.
Okay, cool. So we can just walk through a calculation. I mean, just like these variables here, M, V, they all correspond to some quantity, and we could plug it in. So let's find the motion energy. If a skater was moving at 2 meters per second and weighs about 100 kilograms, so the mass is 100, the velocity or the speed is 2 meters per second. Given this formula, can you tell me what the kinetic energy is? So, oops, you didn't see that. So you have 1/2, and then you plug in 100 for M, and then you plug in 2. So 2 squared, that's 2 times 2. 2 to the power 3 would be 2 times 2 times 2. So this is just 2 times 2. So do you know what this is? So 1/2 times 2, what would that be? So 1/2 times 2. This becomes a fraction, 2/2. Right? And that becomes 1. And then, so these two cancel. Do you see my pointer?
Yes.
And then 2 times 100, what will that be? Javon, 2 times 100. So it's actually 200. And we have 200 units of energy. So let's see an example of how they're related. So let me see. Sorry, I think the screen isn't right. Okay. So let's understand how one energy could become another energy. So we have E equals mc squared. That's a particle at rest. So if there's a particle, let's call it particle 1, the blue particle. And then let's say it breaks up into 2 particles. But let's say the mass of these 2 particles is not half the mass of particle 1. If it was half the mass of particle 1, they would just stay there because energy is conserved. That's a property of the universe, that there's no net loss of energy, there's no net gain of energy. So if particle 1 split into 2 particles with half the mass of particle 1, it would just stay there. But what if it's, let's say, 1/10 the mass of particle 1? So if particle 1 weighs 10 grams and it splits into 2 particles, each having 1 gram, where does the extra energy go? Can you take any guess?
Does the energy have to remain the same all
Yes,
through?
yes. So if energy is remaining the same, but then the mass is a lot different. So this is 1 gram, or this is 10 grams. The blue particle is 10 grams, and it splits into 2 particles, 1 gram each. Then there's 8 grams of energy. And that actually goes directly into this motion. So
And why is that 8? Can you explain that again, John?
why is it 8?
Yeah, help me.
What do you mean 8?
Oh, did I hear hey 8 or maybe I was wrong? Yeah.
I think so it is 10 grams, Rajesh, and particle 2 is 1 gram. So remaining energy is associated with 8 grams of mass.
Oh, yes.
Oh, yeah. I thought the 2, 1, and 2 are the masses. I see. I
No,
see.
No, sorry.
particle 1 is 10 grams and particle 2, which are 2 green ones, they are 1 gram each. So
Okay.
there is a difference of 8 grams. So whatever energy is remaining is related to that 8 grams of rest mass energy. And that he's saying will be converted into their kinetic or motion energy.
So they disappear. So one completely disappears.
Yes. Yeah, so that's the interesting thing. So
Can something disappear like that? Can a mass disappear?
yes, yeah, that's the very interesting thing. So what happens is that as far as we know, our universe is everything that's made out of. You know, if I keep cutting this water bottle, I could keep cutting it, keep cutting it, and then the water bottle will be so small that I can't cut anymore, and that's a particle. And so so mass can't just completely disappear, but it can convert to other particles, depending on how much energy it has. It can't convert if you have an object, it can't convert to an object with higher energy. And this is taking into account the object's rest energy plus the object's kinetic energy. It has to decay into something, it has to transform into something with a lower mass, and then it's extra energy that it hasn't spent to create this new particle, which I'll define particle in very shortly. The extra energy will go towards its motion.
And in daily, do we encounter this anywhere on a daily basis? Probably not, right? Or
I mean, this is happening inside your body. This is happening pretty much
inside our body, this happens.
Yeah, all over the place. Yes.
Oh, all over the place. Yeah.
Yeah, not just inside our body, but yeah, all over.
Yeah.
So the screen, the yeah, all light is also has the same. In order to produce light, you're not completely converting the particles. You're not completely converting, but yes. So all the particles that come from the sun, this is happening in the sun all the time. This is what fuels the sun. Why the sun is burning up is because particles are combining into each other. They are.
So would it be correct to say that radioactivity has this feature at its very basis, where X-ray machine is generating a radioactive
Yes.
energy? Would that be correct to say that?
Yes. Yeah. That is. This is radioactivity.
Okay. Okay.
That's what
Nice.
happened.
Yeah.
Yeah. When the when one mass transforms into another, and then energy gets released. Yes. So,
Okay. And it was not realized until recently, right? Radioactivity. So that's why it's
Yeah.
modern physics, I suppose.
yes. Yeah. And in order to understand it, I mean, you would need to know the E equals mc squared. That's the basis to understand the
Question. Wouldn't it be correct to say that radioactivity was discovered before E is equal to mc square was known? Madame Curie and
maybe, but how was it explained?
it was not explained. Yeah, I'm pretty sure. Yeah, that's interesting. So
Yeah,
in
I
the
don't know.
beginning, when they discovered it, they did not understand, or experimentally it was discovered, but the actual fundamental explanation got much better or clearer once Einstein's
So
equation.
when was actually equal to mc square given?
1905.
Yeah.
1905. Yeah, that's.
And in the, why
yeah,
are you then saying that radioactivity was known before that?
1896 or 97, I suppose, when I think
1890s.
Rontingen, I forget the names. Joan, have you, this probably is history, you might have come across these things. If not, it's okay.
Yeah, I'm looking at the history.
Yeah.
Yeah, I mean,
Oh
only
yeah,
nine years
1896.
before.
I never.
Yeah.
Yeah. Everything happened within a 10-year time period. It's kind of interesting.
Yeah. Yeah, lots of things happened. I think even the Noether theorem, right? When was that? Was that in the early 1900s too?
Yeah, go ahead.
Okay, sorry. Let me get back. Okay. Cool. Was this clear, Joan? Did you do you have any questions about the fact that particles could become other particles or the radioactivity?
Yes, sir.
Oh,
Yeah, just I think I can add a comment to that, from my reading of the history, it was very hard for scientists in those days to believe this, that because they had just got the idea of elements about 100 years, probably 50 years back, no, 100 years, right? Mendeleev classified it in 1850s, but it was just not acceptable to them that an atom could just disappear and become another atom. So when this was proposed, it was not easily acceptable, or it was just counterintuitive. I think that's a bit, I don't want to say it was not accepted. It is just, it was very counterintuitive that one atom can disappear and two other atoms could form. Basic idea of radioactivity was just not there. And
yeah.
struggled a lot with it.
Yeah, but then once you accept Einstein's theory, it becomes very intuitive.
Yeah, correct.
But there's that. So, but then there's the quantum mechanics too. That this is a
Yeah.
quantum mechanic process. So yeah, and then you would say, oh, until the weak.
Yeah, exactly. Until Fermi came into picture in 1930s,
yeah,
it was not considered explained very well, even though there were models explaining it. I think that's what Madame Curie is popular for, I suppose. Like, she contributed significantly to this. Yeah.
So like we said, the world is comprised of some fundamental building blocks. So like Suresh mentioned that these are the elements that if we look at something in the world, we could say, okay, it's comprised of exactly all these things on this chart. These are a lot of things to know. I mean, maybe not so much compared to anatomy and stuff, but these are quite a few. I don't know everything on this chart. I can't reproduce it. But surprisingly, everything is very simple. It's much simpler than this because all these elements are only made of 3 things and combinations or quantities of 3 things. Those 3 things are the electron, the proton, and the neutron. And if we see the proton and the neutron are kind of stuck together in the middle, we call this the nucleus. And then the electrons are floating freely around. So that's a very simple picture. So can I ask a question? Do you think that this is the end of the story? Everything is just made of these 3 things, or do you think these 3 things are also made of some things? Some more things.
I would say, how would we even go about thinking? Or isn't everything made up of something or the other? Like Earth has a radius, proton must be having a radius. If something has a radius, then it's even if it is uniformly there, it's I don't know. Yeah, I think everything should be built out of something.
Yeah, and I mean, I would like to actually take back the statement. There are some other things that we'll see that are not atoms, but yeah. So what?
I had a question on periodic table.
Yeah.
I had a question on periodic table, which might be.
Sure.
So why do we? I mean, we have only 92 naturally occurring elements, I suppose, and artificially we have been going until 118 or something like in that order. Is there a limit to that? Can we keep going?
It seems so from what I know, I think it just gets harder to make the new elements because so what Suresh is saying is that this 103 means that there's 103 protons in here. So when you keep adding more, it just it becomes less stable, but so I think what happens is the stability is due to, or the instability is due to the beta, the weak force, the weak decay. So I think there's always there's a time limit on there. So yeah, I think that, I mean, if you want to try really, I mean, you could keep trying very hard and you could keep constructing these because it takes time for the, and I guess, yeah, maybe if you isolate it, I think you could keep building up.
Like the same thing can be asked about for bigger masses also, like stars. Like, is there a limit on how big they can be? I mean, are they stable? After a while, they just collapse into 2 smaller stars? Is there any such, like how big can something be? I mean, like a star, is there any
Yeah.
fundamental limit, like Einstein's equations or Newton's laws? Do they put a bound on how big a star can be?
Well, I think, I mean, there's a lot of things at play with stars, because then what happens is they could collapse into a black hole, and the black hole can, there's no upper bound to it, as far as we understand. As far as I
Inside a
understand.
star, the fusion cycle can only go up to iron and nickel. That's it. That's their limit.
Yeah, those are the stable. So once they create that, but then if there's if you have like, because I think before the galaxies were huge, you could think of the galaxies as being these huge clouds of, I mean, you could call them stars, I guess, or there might be another term for it.
Like I was thinking more in the context of dynamical, like not even going into black hole and other systems. Like if it's just like Newton's law, like the way Saturn's ring, if I'm not wrong, is not a continuous disk, and dynamically, just because it's not stable, they just collapse into smaller pieces. So similarly, maybe as something grows bigger, it breaks. Or like the same thing with clouds, right? In our sky, how big can a cloud grow into before it is unstable and splits into two? Just curious. Yeah, I never thought about it before this.
Yeah, I would think that, yeah, a star, if it gets big enough, then there would be some fluctuations. I know, like in order to get to a white dwarf, it needs, like, in order to get to like stars can only be so big. But yeah, that's an interesting question. Yeah, so there's even for Saturn's rings, there's is there like an instability period where so there is
Say that again, John?
so for Saturn's rings, there's an upper bound, and there's like some instability period where after, like there's a theory which predicts some because the Saturn's rings are rocks. Correct. There. So is there like a size in which, okay, these things are stable, or is it just kind of?
I think so. Like, for example, I think the statement I have read is, I know this because Maxwell did this apparently for the first time. Before Maxwell's time, it was expected from seeing through the telescope that Saturn's rings must be, I mean, they look very flat and a disk-like structure. And Maxwell, just based on equation, or it was before him, Laplace had attempted that already. So he had already suggested that. And they claimed, just based on analytic equations, that a disk cannot be stable around under the gravity of a spherical object. So it will just collapse into that. And now you're suggesting, is there an upper bound on these masses? I don't know. I haven't done it so carefully.
Yeah. I think now, like with yeah. So.
Like, I think one can even think about the solar system itself, right? Solar system is something that's going around, and each of these planets, like, what does it, why are planets formed? I think all that probably comes into picture. I might be being too naive here. Yeah.
Yeah. I'm not sure. Like, I think I know there's some. I think Chandrasekhar. It's like some. I think a Chandra limit.
Yeah.
So yeah, how massive something can be. So yeah, but I'm not sure. I think galaxy formation, like these structure formations, are still. I don't know. I didn't try learning about it, but maybe they're not understood so well.
Yeah. Not to my knowledge, not at all. Like there's a lot of open questions there. Lots of open.
Yeah. I was at the planetarium 2 days ago, and then they're saying that it was previously thought that our moon was it came from outside our solar system, and then it entered in and then became trapped by the Earth. But then now that they have moon rocks, like they're starting to see that the moon is actually is comprised of the same rocks as the Earth, which would be unexpected if it came from outside the solar system. So there's some new theories that the moon is made of. I mean, is this new? I don't know. I mean,
It is. I think all this probably is 20 to 30 years. There's been a significant progress in the planetary, how the planets were formed, or just Earth and Moon system itself. Yeah, I've read these things at a popular level, like, but I haven't.
Yeah. I did the same thing. Well, the exhibit that I was in.
Yeah, nice.
Cool.
But that tells us that there are so many open questions there, which is not very well understood.
Yeah.
So,
I think, and yeah, even galactic and then beyond.
Yeah.
Actually, they have since like the CMB is getting limited. They're starting to look for like looking at like large scale structure formation in the universe to determine some beginning of the universe type events, if there's any interactions during that time. But that's the whole universe is also not understood. Okay, so can we break these up further? Well, it turns out that the electron isn't broken up farther, but then the proton, the neutron, they're broken up into these further particles, which now we think are as fundamental. And what's pretty interesting is the mass of the U. So there's two particles that the proton and the neutron are made of. The proton has 2 U particles and 1 D, and the neutron has 2 D and 1 U. The U stands for up, the D stands for down. So the mass of the proton, the mass of the U is 2. We call this MeV. That's just a unit of mass. The D is 4 MeV. So in the proton, 2 U's and 1 4 will be a total of about 8 MeV. But then we see that the mass of the proton is 928 MeV. So how can this be if it's only made of 3 particles and their masses sum to 8 MeV? Why is this whole thing 128 MeV? And if you see that there's these curly, these circles, these spirals, those are actually, there's a force binding them together. So they're bounded by a force. And then these springs, they resemble the force that it's bounded by. And then like any spring or rubber band, when you pull it apart, there's some tension. And then this tension has energy in its form. So this is the third form of energy, and we're gonna call it potential energy. The more you stretch out the rubber band, the more potential energy it has. So the more that these quarks are pushed away from each other, which they should be, because the electric charge differs between them. There's some electric, negative and negative charges repel, positive negative attract. So they're being pushed away from each other. And it's responsible for most of the mass. And so this tension or potential energy, we saw that energy equals mass. So potential energy gives mass to the proton. So, and these are moving very fast, so it's hard to contain them. So any questions? Okay, so we went from here, all these elements, plus some other things that we don't see, that are not part of our daily life. All made of only these particles. So they're color coded, and they're much less, so they're easier to remember than all the elements. So these give rise to forces. So this force over here, these spirals are, this is called the strong force, and it's given by the gluon. And then the electric forces have the same exchange diagram with the electron. And then the Z and W are responsible for decay. If you didn't catch all that now, I will go over it soon. And then in the purple are the particles that make up other particles. So you would say they can't be seen separately. They have to be seen in clumps or pairs. And then these are the particles that ride solo. You always see them separately. Very rarely do you see them, or they don't need to be. They're not necessary. It's not necessary that they're bound to other particles, but as you know, for the electron, it's bound, and many times it's bound to the proton and the neutron.
So
the
the
other
proton
table
and
was,
the
yeah,
Yeah.
go ahead, Prachi. Sorry.
proton and the neutron will be only made out of U and B. No, U and D,
Yes.
right?
Yes. Yes.
And rest everything is like some exotic stuff, which is not on the periodic table, right?
Exactly. And that's what I was talking about. Like, that's exactly what I was talking about when I said, oh, there's some objects that exist that's not in the periodic table.
Yeah, so basically like U, D, and E are the ones which will make up an atom, and
Yes.
you can say that G is there as binding, the
Yep.
spring that you are showing, that is the binding, and that's it, pretty much.
Yes. So this is
In
atom.
the laboratory, have they built anything other than atoms that can survive for more than a second?
So these particles, they typically can't survive more than a second. They're very the top and the bottom, they're very extremely quick. Like, they can't even form bound pairs with each other, or if they did form a bound pair, like, they can't even undergo a single orbit. So these particles were found but what's required is you need a very, very large particle accelerator, many kilometers long. And then when you have this huge, do you know how big the LHC is? How many kilometers?
I know that it goes through 3 countries.
Yeah. So LHC. Yeah, so the circumference is about 17 miles. And yes,
It's
it
about
goes,
30 kilometers, right?
yeah. So it's a huge machine, and it actually goes through, let's see. Here's where it goes through.
Yeah, that's, I think, a picture of that.
Yeah, so here's Switzerland and France,
Oh, so it's only 2 countries, not 3.
I think. Yeah.
Okay.
Yeah, it looks like it's only 3. LHC. Cool.
Nice.
So yeah, that was a very good point. And then 2 electrically charged, like 2 positive charges, how really what causes the force in our models, or the best the models that work very well. What we could see, what exchanges, let's say the electric force is this care of the, they just exchange a particle. So there are 2, let's see. So these are 2 charged
I think
particles.
we lost Juan just for, I think.
Okay.
Yeah, keep going. Yeah.
Okay, so there's 2 charged particles, and then they exchange this photon. So that's what causes the force at a very fundamental level. That's a picture that works very well. And then so we have the strong force, the electric force, and then the W and the Z boson are responsible for the decays, like they're responsible for turning one particle into another one. So are we missing another force? And I didn't Google this. I just wrote this statement. It might not be the most famous, but we have gravity. And there's the, oh, is Jovan back? Oh, no, she just left.
That's okay. You continue. Yeah.
Okay. So Jovan, so what we said was these, as far as particles go, we found these 4 particles that describe 3 forces, but it's leaving out the gravitational force. So we haven't explained this with particles. We haven't, the electromagnetic force was explained with the gamma particle, the gluon. The strong force was explained by the gluon, what we just saw, pulling together the U and the D quarks. And then the weak force was the other 2 particles, which were responsible for just some mass converting into another mass. So let's see. So why wasn't gravity included? And so what a part of the reason was that we were treating these particles as points. So even though I drew a ball for the electron, it should be more like this, a dot, but then this dot actually has some width to it. So if you could just imagine like a 0-dimensional point that has no area or volume. So if I were to draw an accurate electron according to these models, we wouldn't be able to see it. There's no width or height to it. But what happens, and gravity, it's proven and shown that you can't have a point particle picture of gravity.
Why is that? Say it again, like, I mean, make it clear.
Yeah, I mean, there are some theorems, but yeah, it's kind of, I mean, you could see it from the expand, like when you have essentially because the gravity. So when you have gravity, it's
Like,
coupled.
like
Yeah.
the statement you're making is that gravity does not accommodate point particles.
Particles, yes. So I mean, essentially, it has to do with so over here, like you saw that the interactions were at a point. So we have 1 point particle. So we just imagine this being a point particle, and oops, over here. And you could imagine this wiggly line also being a point particle. So when the points meet, we could get some interaction strength from it. So we could reproduce the interactions that are seen. But then if we have some, we could call it grav or Q. How about this, the P particle? And that represents gravity. And then when it gets really close, if it gets too close to two massive objects, then it would, we can't describe the physics that that we see. We can't describe the moon orbiting the Earth, and we don't get anything that would make sense. So yeah, it has to do with the fact that let's see.
It's okay. I guess go ahead. I'll try to
Sorry, yeah, I mean,
review the statement.
so-
I was just like trying to
Yeah.
register the statement, what it means to say.
yeah, that's right. Because I mean, you can see it from like when you do like the perturbative expansion around when you have the define the interaction to be local, and then at one point, and then you see that there's the coupling that just keeps getting bigger and bigger, and essentially you need to have infinitely many terms in order to get something that's produced by experiment. Whereas in the other perturbative forces, like the photon and these forces, you get a well-defined expansion of the point interaction, and then this, you still need issues running, similar issues are ran into, but then especially when the particles are there's a lot of potential energy. But then because they have this natural spacing, when the coupling becomes strong, it's very natural to consider it to be the interactions are more spaced out and on the lattice. So
Okay, yeah, that's fine. Like, I mean, you can introduce it. Then, like, I mean, you're bringing in the string theory now, right? So,
not really. I think it's kind of over. So I just wanted to make some quick statements.
okay, go ahead. Yeah.
But this is supposed to be, however, this requires the universe to have 9 spatial dimensions, and we haven't seen these spatial dimensions. And so right now we have the three space dimensions, and then if you look very closely, there's these other dimensions coming in. Like you could think of, oh, maybe this ant only sees 1 dimension, but then if you look very closely, they're curled up. So this has to come with this picture of having just an extended objects to have smear out the point interactions. So maybe space is also made up of indivisible chunks, and the area, you can't have a small area, just like how you can't keep dividing the water bottle. You can't have an area that becomes infinitely small. Instead, that there are these finite chunks that you can't divide up anymore. And the picture that how this picture was conceived is related to the last point about not having where gravity can't be a point-like particle interaction, because then you'll have divergences, or you'll have the theory won't be predictive at a point. So what happens is you don't view it as an interacting theory, but you just you smear out, or you kind of extend the properties of the gravitational field over these lines, and then you could construct your theory that way, and you could do it in a background independent manner, so you don't need actually so instead of having a space in which the particles interact, you just have these objects which make up a finite, you just have these finite chunks of space in which you can't get any smaller than that. So in that sense, they're also kind of like Legos. And then both ideas might be wrong, but we don't understand gravity as fundamentally as the other forces. and many people and groups today are working on it. So yeah, it's very hard to fit the gravitational force and the other within the other pictures. So any questions?
So maybe a trivial one, like, did you have your talk's title as particle physics or modern physics? I forgot that.
Modern.
Okay. So maybe what is the difference between modern physics, if you can tell, versus what was earlier in comparison?
You mean modern physics today versus?
No, not today, like why it was called, like there is a clear distinction that occurred right in 1900s, beginning 1900s. And,
Yeah. So
and before that, we have almost 300 years of physics, I would say, at least the modern science. Like, I mean, of course, physics has been going all the way to Greeks and even before, whatever you want to continue. But what we call as the modern scientific revolution, that is started with the Galileo, right? Pretty much. Copernicus.
yeah, so I think, I mean, they're operating on different paradigms.
Yeah, so exactly that is what I am trying to bring out. Like, what do you say is a paradigm? What changed?
So there was an absolute notion of space and there was an absolute notion of time that Galileo and Newton and Maxwell were operating with. And there were some tensions, especially between the late 1800s, between Maxwell's theory, the theory of electricity and magnetism, and then Newton's theory. So the tensions had to do with the notion of some absolute space and absolute time. And what happened in the 1900s was that Einstein had determined that space and time were not fixed, but they change dynamically. There was some time was a relative concept, and space interacted with matter, and I was able to change, like the space is what gives rise to gravity. So if you have a very massive object, then you have gravity, and then that changes space and the way it bends space, you could say. And then another issue is determinism. So before then, there was a notion that if we knew the state of the system at one point, we could determine exactly what will happen at a later time, predict what will happen, but then with quantum mechanics, there's some inherent uncertainty in the system that can't be removed by systematic progress. So you can't, there's nothing you can do to get rid of this uncertainty. So it introduced the notion of some non-determinism or some indeterminism, where now an electron, so if you have a ball and it's very small, and then you prepare it in the exact same way, like you have 5 balls prepared in the exact same way, and you kind of push it in the exact same way. One ball will end up in a different place than the other ball. Like there's no way to have certainty with which something that one path will go. Whereas in Newton's theory, you have complete certainty, where if you throw this ball at this angle, it will definitely end up here at this time. That's not the case in quantum mechanics, but what happens if you do this enough times, you get some average value that, so it has the most likely, I mean, it will most likely obey Newton's equations, the classical equations, but there's still some level of indeterminacy.
So basically, yeah, you already focused on the 2 important stuff. Yeah, it has to do with the relativity and the uncertainty, basically. So there is another thing, like, I mean, can you go to the chart which had all the particles up there? Yeah, I think make it bigger. It's too tiny. Yeah. So what we see around us are generally atoms, right? Elements, and then molecules are built out of them, and then bigger structures are built out of molecules, polymer chains and all that, and then they become wood or whatever you see like around us. And they are only made out of this U and D and E and the G because of the force. So what are the rest of them doing?
So so you could find these particles. Okay, these are, you will find them very often. These are constantly coming out of the sun. So I think actually, like in your fingertip, like 1 billion of these neutrinos pass every second. So they are floating around. I think I think there are energetic, like they're
like let's consider it this way. I mean, okay, that's probably a wrong question to ask, but we perceive things which we are able to eventually see either by, like, I mean, let's say our own eyes or like a microscope or anything. And I mean, normally like elements are useful, right? Like we build things out of them. But what are these rest of the particles actually doing? Like, I mean, why are we not, I mean, of course they are useful. I know that they are useful in some sense, but what are, like, why are we not able to maybe make something out of them, let's say?
So they, okay, so So they are constantly interacting with these weak forces, which are causing them to decay back down to the U and the D. So if we were to make something, I think stars, like some stars might, they're energetic enough, and then some galaxy accretion. They're also, so you could find them in there, but they're not going to live for very long for humans to. I don't think humans can do anything practical with these. I don't see how you could isolate them from the, because yeah, you can't isolate them from the Z and W bosons, so they will undergo decay.
But
think
just
let us
because they're found in the,
finish-
yeah, go ahead, Rajesh.
Go ahead, Prash. No.
No, like, I mean, the point is like, I mean, we know of their existence because we have seen them in laboratory or the experiments and other places. And we do know how to make sense of like what exactly they are doing or where they are. But then it just feels like, oh, it's almost like the periodic table that, oh, you cannot build higher than that because they are unstable and they will decay into the smaller one and smaller one. So why can't we just live with the first column here and the orange column and forget about the rest?
I mean, you can, and I think that's what the government, like that's like the government will say the same thing. That's why we're not seeing any more particles. So yeah, because the government's asking your question, why can't we just live with what we see? Because there are particles beyond this. I mean, I think we're pretty sure there's some even anomalies in like the muon, the moment of the muon. So I mean, these are strong hints that there are more particles.
Mhm.
But we have, I mean, we need money to build detectors to find them. And I mean, we could find them in LHC. I mean, there's still possibilities, but we have a much higher chance, and we could possibly find much more if we build periodic colliders. But then, but then there's a question of, okay, why do we need these? I mean, but I don't know, maybe if, you know.
No, I'm just going by
Okay.
the fact that, like, I mean, if they do not have a long life and they will decay into like the smaller ones, then why not just build the structure out of the smaller ones and say that, oh yeah, if you combine these ones, you will get the higher.
Oh,
and
because
of it
you
and
can't-
this and that.
You can't do, you need yeah, you need to have a lot of energy to have these downs decay into the strange. And that's what's happening. So at the LHC, that's what they're doing. They're taking the lighter particles that are stable, and then they're giving them a lot of energy, and then they're building the bigger particles like the charm, strange, top, bottom.
Yeah, but you build it and then how long does it stay before it decays back?
Yeah, fractions of a second.
Yeah.
Like
Yeah,
10,
so
yeah,
like
much
my only thing is that, yeah, I do know the need of like all these like the boxed ones that you have put up there. They have been seen and they do describe some property which cannot be described with the UND alone.
Yeah.
But at the same time, yeah, it feels like if we are just talking about the fundamental particles, if everything has to decay back to
I see.
UND and E and nu. So then, yeah, something.
But then you could also say that like symmetry is fundamental, like, objects don't need to be fundamental, but properties of theories are fundamental. Like
Yeah, so
conservation
that's
laws.
another way of thinking about it, that particles are not fundamental, but symmetries are.
Yeah,
Yeah.
like these laws of physics.
Let's have the discussion going, but I'm going to officially close the session so that we have a limited, just for keeping the time in control.
Yeah, thank you, John.
Yeah.
Thank
Sorry, I
you.
couldn't answer
John.
more questions.
This is really